vibrations of an Euler beam between rigid obstacles with perfect unilateral constraints. So this is a joint work with my colleague Yves Dumont from Montpellier. So we begin with an elastic beam, which is clamped at its left hand and which can move freely at its right hand. We denote by y the vertical deflection of the axis of the beam, and we assume that the motion is planar. So the equation of motion is given by this partial differential equation. The second derivative of y with respect to time minus the first derivative of sigma with respect to x is equal to g, where g is some external load which is applied to the beam, and sigma is a stress tensor which is proportional to the opposite of the third derivative of y with respect to x. Since we have assumed that the beam is clamped at its left hand, we have the following boundary conditions at x equal to 0. So the displacement is prescribed and is a given function of the time t, which corresponds to the motion of the vibrating wall. And the first derivative with respect to x is equal to 0. On the contrary, for the right hand of the beam can move freely. So we have no moment and no pressure on the right hand of the beam. Now we modify slightly the physical setting by adding two rigid stops at the right hand of the beam. So now the displacement is limited by the presence of the two obstacles. And for this obstacle problem, we will assume furthermore that the stops are perfectly rigid, so we have no penetration of the beam into the stops. So the new boundary conditions at x equal to L are now given by the first condition. Still, we do not have any moment. But we have no limited possibility for the displacement, the vertical displacement of the right hand of the beam. G1 and G2 are the two values which characterize the position of the obstacles. And since we assume that there is no penetration of the beam into the obstacles, the contact is modeled with Signorini's complementarity conditions, which says that the stress tensor is still equal to 0 when we do not have any contact. Otherwise, if we have a contact with a lower obstacle, for instance, we have a non-negative stress tensor. And if we have a contact with the upper obstacle, we have a non-positive stress tensor. So all these inequalities for y and for sigma can be summarized in this relation here, where we have introduced the subdifferential of the indicator function of the interval G1, G2. So now, starting from this mechanical description of the problem, we can derive a mathematical formulation. So we get a variational inequality. Of course, we have considered another unknown function, which is now denoted by u, in such a way that we get some homogeneous boundary conditions at x equal to 0. So more precisely, u is defined as y minus some polynomial function of x times f of t. And the polynomial function of x is chosen in such a way that u satisfies these boundary conditions at x equal to 0, and the same boundary conditions as y at x equal to L. So with integration by parts with respect to the time variable and to the x variable, we get all these terms. And the inequality comes from the Signorini's complementarity conditions at x equal to L. So since we have here some second order derivative of u with respect to x, we can expect the solution to belong to H2 of 0L. And so if we consider furthermore the boundary conditions at x equal to 0, we can define the functional space V in which we will look for the solutions. We denote by H the functional space L2. And we have introduced here a convex subset K of V, which correspond to the functions of K which satisfy the unilateral conditions at x equal to L. So for this problem, we know that there exists a solution. The result has been proved by Cutler and Schiller in a paper published in 2001. And the technique of the proof is based on a penalty technique. So more precisely, they relax the constraint and they replace the Signorini's complementarity conditions by a normal compliance approximation, for which the stress tensor is now defined as a function of u with this relation. So we can observe that the stress tensor is now proportional to the penetration of the beam into the obstacle at x equal to L. And we have a coefficient of proportionality which is given by 1 over epsilon, where epsilon is a penalty parameter which is assumed to be small. So the smaller epsilon, the smaller the penetration, and at the limit, when epsilon tends to 0, we get a solution of the unilateral constraints problem P. So this is a very nice mathematical tool in order to get an existence result, since it can be related to the Yoshida approximation of the maximal monotone operator given by the subdifferential of the interval of the indicator function of the interval G1, G2. But this is also a nice theoretical tool to get approximate solutions, since, of course, we get a penalized problem with this relation between sigma and u, which is now described by a variational equality. So we can solve this variational equality by any kind of standard technique. But of course, from the computational point of view, there is some drawback, which is due to this coefficient here, 1 over epsilon, which creates a very stiff term. And of course, the smaller epsilon, the smaller the penetration, so we get a more accurate approximation of the non-penetration condition. But of course, we need to choose also smaller values for the space and time discretization parameters. So for the computational point of view, this is a very expensive technique. And furthermore, at the end, we get a numerical approximation of the penalty approximation of the original problem. So we have two steps in the discretization. So motivated by computational issues, we would like to propose another kind of discretization of the problem, which will be able to deal with directly with the unilateral constraints. So we begin by another formulation of the problem, which is slightly more general, since we have replaced the previous definition of K by something which allows us to take into account any kind of physical setting for the obstacles, with two mappings, G1 and G2, which characterizes the obstacles and which can take infinite values. So with infinite values, we can consider that we do not have any obstacle at the point X. Otherwise, when we have finite values, we have an obstacle at the point X. So now, starting from this more general problem, we begin the discretization by some space discretization. So we replace the functional space V by some finite dimensional subspace VH. And of course, we have also to replace the subset K of V by some convex subset KH of VH. So reminding that K is a convex subset which takes into account the constraints, we would like to define another convex subset which takes into account the constraints but at the discretized level. So we choose to consider the constraints only at a finite family of test points which are denoted as XAH. So of course we get the Galerkin approximation of P simply by replacing V by VH and K by KH. So we have once again a variational inequality, but now the unknown function UH takes its values in VH, so we can describe it by using a basis of VH, and we can reformulate this approximate problem PH in a matricial form. So more precisely, if we denote by phi1, phi2, phi jh the given basis of VH, we introduce the coordinates of UH in this basis, which is now denoted as U bar H. So this is a new unknown function, which is a vector-valued function in RJH. And the variational inequality is rewritten as a differential inclusion, a second order with respect to time differential inclusion. And now the constraints are taken into account in terms of the coordinates of UH. So we get a convex subset, which is still denoted as KH, but now KH is a convex subset of RJH. And it corresponds once again to the unknown functions which satisfy the constraints at the discretized level. So that we get these geometrical inequalities for the coordinates of the unknown functions. So now looking at this new formulation of PH, we can obtain another interpretation of this space discretization of our original problem. Indeed, we can interpret U bar H as the generalized coordinates of a discrete mechanical system. And this kind of differential inclusion correspond to the description of the dynamics of a finite dimensional mechanical system under the constraints given by the convex set KH. So having in mind this interpretation, we can now introduce the time discretization of our problem P simply by applying the time-stepping schemes which have been developed for unilateral constraint problems for discrete mechanical systems. So if we denote by delta t the time step, we propose the following fully discretized approximation of our problem. So the approximate positions are updated in a quite classical way with respect to the approximate velocities. And at each time step, the approximate velocities are updated by solving this inequality under the constraints which are given by this condition here. So V bar Hn should belong to the tangential cone to Kh at U bar Hn, where the tangential cone is described here more precisely. So we can observe that, in fact, here we take into account the constraints at the velocity level, since the constraints is now given for V bar Hn. And we have a linearization of the constraints around the position obtained at the previous time step. So for the numerical point of view, this kind of linearization is, of course, very convenient, since it gives us only linear constraints, and we can deal with this kind of constraints very easily. We can observe also that we have introduced in this fully discretized problem a parameter theta, which should belong to the interval 0, 1, and which plays the same role as the theta parameter in the theta methods for differential systems. So, of course, if we look to this inequality, it seems to be difficult to be solved, since here we have something which looks to be an implicit term with U bar Hn plus 1. But indeed, if we replace U bar Hn plus 1 by using the updating rule for the approximate positions, we can rewrite once again the fully discretized problem as a minimization problem, which is a quadratic minimization problem under linear constraints. So the matrix which appears here is given more precisely in this form. So it is a symmetric definite positive matrix. And at each time step, we get a unique solution for our fully discretized problem. Furthermore, this is a linear quadratic problem, and we can use standard optimization tools in order to solve it at each time step. So now, of course, we are interested in stability properties for this algorithm. So we introduce the same kind of assumptions for the data as in the existence result proved by Cutler and Schiller. And we assume classically that VH is an approximation of V. Then for the approximate position and velocity UH0 and VH0, we introduce these two assumptions. And we get this inequality, which gives us the stability property, and which gives us unconditional stability property whenever theta is greater than 1/2. Otherwise, we get some value, delta TH, which gives us only conditional stability property. So this difference between unconditional or conditional stability property is can be interpreted in the same way as for the theta method for differential systems. This is exactly the same kind of result. So now, starting from this inequality, we can get a priori estimates for the approximate solutions. So more precisely, we define the approximate solutions by a linear interpolation of UHN and UHN plus 1 on the time interval n delta t and plus 1 delta t. And the previous estimates gives us an a priori estimate for the approximate solution in this functional space W. So we can pass to the limit when the time step and the space step tends to 0, at least for subsequence, and we get some weak star convergences. With Sobolev embeddings, we infer some strong convergence in the space of continuous functions. And so we get at the limit the right initial condition U0 for the limit function U at t equal to 0. So for the mathematical studies, the last step is to prove that U is a solution of problem P. So as usual, we would like to perform some discrete integration by choosing appropriate test functions in the fully discretized problem and pass to the limit in order to get once again the variational inequality. But of course, we have first to prove that U satisfies the unilateral constraints, which means that we need to prove the feasibility of the limit function U. So this step of the proof is not so obvious, since we have to keep in mind that at the discretized level we have chosen to take into account the constraints only at a finite number of points, a family of test points which was denoted XAH. So of course, if we want to recover at the limits conditions all over the length of the beam, we need to introduce some assumptions on the choice of this family of test points. So more precisely, we introduce these two conditions. So for any value of x along the length of the beam, we assume that there exists a sequence of test points which converges to x, and such that the values of G1 and G2 converge also to the value of G1 and G2 at x. So at the first glance, this second condition may look as a direct consequence of the first one, but indeed it is not, since we do not have introduced any continuity assumption for G1 and G2. So of course, when G1 and G2 are two continuous mappings, we only need to check the first condition, which is trivially satisfied if, for instance, we choose the family of test points as the space nodes, for instance. Otherwise, we need to check also the second condition, and in order to be sure that both conditions are satisfied, we can choose, for instance, the space nodes, and we add the discontinuity points of the mapping G1 and G2 in order to ensure that the second condition is also true. So these two properties are not really restrictive for the geometrical setting. We always manage to satisfy them. And under these assumptions, we can prove that U satisfies the unilateral constraints, which means that we have the feasibility of the limit. And then with standard techniques, we get the conclusion that U is a solution of our original problem P with the perfect unilateral constraints. So of course, for the numerical aspect, this is a convergence result for the numerical techniques that we have proposed. But as a byproduct, we obtain also an existence result for the more general formulations that we have chosen to consider. And in such a case, we have some extension of the existence result, which was proved by Cutler and Schiller. So as a conclusion, I will present now some examples of implementation. So for the computations, we have chosen a steel pipe with a length equal to 10 meters, an external diameter given by 1 centimeter, and a thickness equal to 0.5 millimeter. And we begin with punctual obstacles at the right hand, so the physical settings that I have presented in the first slides of the talk. So in this geometrical setting, we know that we can apply the normal compliance approximation in order to get approximate solutions. And this gives us a benchmark in order to compute the results that we will obtain with our numerical algorithm. So for the computation, we choose space discretization given by P3 Hermite finite elements, and time discretization chosen with a parameter theta given by 1/2, which corresponds to the Crank-Nicolson method for differential systems. Here we have only a discontinuity at x equal to L for G1 and G2, so we can choose the space nodes as test points, XAH, since indeed the right hand of the beam is one of the space nodes. And then, we have performed here we have computed the trajectory of the right hand of the beam. So on the left picture, we have plotted the trajectory obtained with our numerical algorithm, with a time step equal to 10 minus 5 and 160 space nodes. And on the right picture, we have the result obtained with a normal compliance approximation with the same time step, but with penalty parameter epsilon given by 2 times 10 minus 7. So we can see that the global behavior is the same, but here we have some numerical instabilities which appear when the time grows, and which are due to the fact that epsilon is not small enough to accurately approximate the unilateral constraints. So indeed, if we compute the maximal penetration into the obstacle with a normal compliance approximation, we get something which is not so satisfying. Of course, with the scheme, we have also some penetration in the obstacle, since we have chosen to take into account the constraints at the discretized level only in terms of the velocities with the linearization of the constraints. So we cannot prevent the approximate positions to violate a little bit the constraints. But here we have something which is 100 times smaller than what is obtained with the same time step with a normal compliance approximation. So we have to keep in mind that for the normal compliance approximation, the smaller epsilon, the smaller the penetration. So we have performed other numerical tests with smaller and smaller values for epsilon. So of course the penetration decreases, but the smaller epsilon, the smaller also the value of delta t, since it has been proved that for the normal compliance approximations, approximate solutions penetrate into the obstacles during time intervals which length is of order square root of epsilon. So of course we need to choose a delta t smaller than this characteristic length. And for this value, for instance, of epsilon, we need to choose some values of delta t given by 10 at the power minus 7. So of course, the smaller delta t, the bigger the CPU time. And we can see that for values of the penetration which are of the same order as those obtained with the scheme, we need to choose delta t 100 times smaller, since here we have still delta t equal to 10 minus 5. And the CPU time is more than 150 times larger. So next we have tried to compute solutions with smoothly shaped longitudinal obstacles, which are described by these two mappings, G1 and G2. So the obstacles are given here by the blue lines, and in the black we have plotted the position of the pipe for different values of the time t. So once again, we have chosen 160 space nodes, a value of theta equal to 1/2, but here delta t is rather big. So of course, with this rather big value of delta t, the penetration is not so good. And here we have to keep in mind that the penetration is small at the space nodes, which are the test points for the unilateral constraints. But here, due to the convexity and concavity of the obstacle, compared to the shape of the basis functions for the P3 finite elements, we get something which is much larger if we compute the maximal penetration all along the beam. So indeed, this is the worst that we can observe, and it should be better if we decrease the value of delta t. Thank you for your attention.
Thank you. Any other questions? Remarks?
Thank you for your nice presentation, but I have a question or a remark. So it is very important to consider a higher order problem with a beam. So you have these P3 elements, finite elements, and so you have this non-conforming approximation. Do you also include your analysis the error by quadrature? You have to use some quadrature rules, and so you get additional errors.
You mean that we can use a quadratic rule for the time discretization?
Time and space discretization. Yes.
We have tried for the space discretization to use B-spline. But for the time discretization, the idea was to use, well, let's go back. To use appropriate schemes to compute a solution of this kind of problem. So we know that for this kind of problem, if we use this kind of schemes, which are here, given in this paper, we have convergence when delta t tends to 0, when we have a given space discretization. So the point here was not to get only the convergence when delta t tends to 0 for a given space discretization, but to have the global convergence when the two parameters tend to 0 at the same time. And it is useless to get a better integration of the problem pH with respect to time, since due to the shocks, when we have a contact, we lose any order of convergence. So as long as you have a free flight without contact, you can get any order of convergence if you choose an appropriate integration rule for the time discretization of pH. But when you have the first contact, then you lose everything. And there is no need in choosing a better time integrator than this first order integration in some sense, since the theta method is, except for the value of theta equal to 1 over half, a one order method for differential systems. But we have tried different values for theta. So here we have chosen theta equal to 1 over 2, because it was the Crank-Nicolson method, which was the best one in some sense for differential system in the family, which is chosen here with the theta parameter. But we have also tried to choose theta equal to 1, which is the analogous of implicit Euler method. And the results are the same. We do not improve the results in terms of CPU times or in terms of penetration errors. So really due to the fact that as soon as we have contact, we lose the order of convergence of the time integrator that we introduced for the space discretized problem.
What regularity do you need for G1 and G2?
Sorry?
What regularity do you need for G1 and G2? So just continuous functions? Or?
No, you don't need to have continuity. You can
Okay,
choose anything you want.
Mm-hmm.
The only condition that you need to check is this one. So it is trivially satisfied if G1 and G2 are continuous. This is also trivially satisfied if you have a finite number of discontinuities. But if you have an infinite number of discontinuities, it may be a little bit difficult. But in most cases, the geometrical setting is not more than a finite time discontinuous for the obstacle. So it's difficult to imagine something which has an infinite number of discontinuities for obstacles in a real physical setting. But you don't need to have continuity. So.
Any other question? No? Let's thank Laetitia again.